Yeah, we just finished day 10, so now it's time for day 11. So let's get set up for that. Oh, I've forgotten how to do this. Again, the mod, right? Yep, there. Boom, boom. Like that, like that. We copy this, change the 0 to a 1, and add it here. Day 11. Great. And then try to build. Oh, right. And then that fails because this doesn't exist. So we do a code action to create the file. We then jump to it and do AOC. Is it AOC lib? Nope. AOC? Yeah. 2016. Day 11. Okay. And then we should try to build. Oh, and then bacon. Test. Oh, right. And we want to change our toml to day. There's a 10. There it is. Change to 11. And then, so now we got tests for day 11. Beautiful. Okay. Now let's actually look at what the problem is. Advent of code day 11. Radioisotope thermoelectric generators. Come upon a column of 4 floors that have been entirely sealed off from the rest of the building except for a small dedicated lobby. There are some radiation warnings and a big sign which reads Radioisotope Testing Facility. According to the project status board, this facility is currently being used to experiment with radioisotope thermoelectric generators, RTGs, or simply generators. They're designed to be paired with specially constructed microchips. An RTG is a highly radioactive rock that generates electricity through heat. Okay. What are we trying to do? What's the minimum number of steps required to bring all of your projects to the 4th floor? You know what? I vaguely remember this one. This was a very difficult one, as I recall. And most of it was trying to figure out how to model. Okay, so let's see what the rules are. Experimental RTGs have poor radiation containment. Chips are prototypes that don't have normal radiation shielding, but they do have the ability to generate an electromagnetic radiation shield when powered. Unfortunately, they can only be powered by the corresponding RTG. Okay. So this is the goat, or the fox, the seed, and the chicken boat problem, right? If a chip is ever left in the same area as another RTG and it's not connected to its own RTG, the chip will be fried. Okay, therefore it's assumed you will follow a procedure to keep chips connected to their corresponding RTGs when they're in the same room and away from other RTGs otherwise. Microchips sound very interesting and useful to your current activities. I bet they do. Okay. As a security measure, the elevator will only function if it contains at least one RTG or microchip. Okay, so we have to make a move, in other words. We can't not make a move. The elevator always stops on each floor to recharge. Okay, so that means every floor, and this takes long enough the items within it and the items on that floor can irradiate each other. You can prevent this if a microchip and its generator end up on the same floor in this way, as they can be connected while the elevator is recharging. Right, so basically we're just moving things up and down. And E is the elevator. I guess when you enter the containment area, the elevator will start on the 1st floor. For example, suppose the isolated area has the following. Okay, so is this what we have to parse for our input? Let's see what our input looks like. Yeah, so we have basically parsed this kind of thing for the input. All right. Let's generate our input file. Promethium, cobalt, curium, ruthenium, plutonium. Okay, so it looks like there's 4, right? Promethium, cobalt, curium, And ruthenium. Oh no, 5. Plutonium. Oops. I clicked on the scroll bar. Plutonium. So 1, 2, 3, 4, 5 different pairs. We want to parse this or just put it in directly? I guess we can parse it. And then this is the test input, which we can just put directly into the file, right? As a static string. Const test data stir is equal to this. Yeah, okay, that works. And then we can just in the parts we can parse test data. So I think the biggest issue, right, is how do we model this? We have microchips and generators. Oops, microchips and generators. We have floors. Right, there's 4 floors, and then there's the entire building. So I wonder if that's the way we want to model we have a struct building which contains, I don't know, a vector of 4 floors. And then a floor contains microchips or generators. Should we just create a vector of items? Like that, and then we can say enum item is either a microchip or a generator. And then as we go through here, we can just create the floor. So let's see if we can, if this is a reasonable starting point for generating what we parse out. Right. What I'm thinking is once we have this thing modeled correctly, then we use the building as a state. And we use, I don't know, we use some sort of backtracking algorithm, or, oh, we could use Dijkstra, right? If we model each one of these as a state, we can use Dijkstra to figure out how to go from the starting state to the ending state. And this does this. Oh, okay. So this shows us step by step how to solve this reduced problem with only 2 different elements, H and L. Hydrogen and lithium, was it? Hydrogen and lithium, yeah. Okay. So how do we parse? We can ignore the first floor contains, but I see here there's a nothing here. So we can either look for a nothing and then skip it, or the letter A, or maybe let's take a look here. Is there an an? There is no an. So all of these things start with a consonant sound instead of a vowel sound. Okay, so that simplifies things a little bit more, right? We can just look for the word nothing, or look for the letter A on 0, 1, 2, 3, 4. Oops. So this let lines is equal to AOC lib read lines input 2016-11.txt, and then we're going to use test data. Let lines is equal to test data split new line map x to x2 string collect vec string. I think that'll give us all the lines, right? And oh, we're running. Let's just do a run here. Yeah, unsolved, unsolved. So now we can actually do some printout here. We can see if we got our lines correctly. Println. Oops. This should be a dot. Okay, so here are the lines. That seems to have worked. Okay, good. Now how do we parse this out? Let's do this. And then up here we can take a look at that. Make that a little smaller. There. Okay. So each line is going to have its own floor. So let's... the way the buildings work is that we just have a vec of floors. So we can either push an empty floor if it says nothing. So that's the easy case, right? We can say for L in lines. If, oh no, we want to split. Let words equals L dot split on space. Collect vec string. Right, and then, okay. If words of, what was it? 0, 1, 2, 3, 4. Can I compare it this way? I have to aster continue. Oh no, we want to push an empty, oh, we need a building. Okay, let mod building equals building. I guess I could create a new function for it, right? Let's do that. Impl building. Or we could just derive default. That's probably easiest. Oh, right. The building also needs an elevator. Right? Because the elevator goes, it's here. Yeah. Okay, so we can just put size. But the default derive still works. Okay. And then we can just say building, oops, push, vec new. And it'll figure out the type of that. And then I just want to print out the building here. If it's not nothing, then we're going to parse this thing out here. We have, it's either going to be a word with a dash for the microchip thing, right? The generator doesn't have a dash in it. Oh, and there could be more than one. Right, and in fact, if we look at our test input, I'm going to look at it again. Here's 1, 2, 3, 4. So we have to keep looping over the words. Loop? Maybe? And then, oh, yeah, I want to create an iterator. Let iter equals words, iter skip 4. This is still an iterator, right? Skip. Can I do that and then just continue to iterate over the words? Let's try this. Println word equals this, iter next. But we need to be able to break. Let next equals iter next. If next is none, break. This is just test code right now. I just want to see how this works. To see if we can work our way through it. Nope, doesn't like that. Oh, this split create, okay, that's fine. That means we don't have to do this. Oh, building a floor. Expected struct floor. Oh, right, okay. I thought I was pushing a... Yeah, this is going to take all stream just to do the setup, right? And now we can't print next. Option, oh, unwrap. And then we can't print the building. Oh, okay, yeah. Let's derive debug on all these guys. And then this needs to be mutable. Yeah, okay, so now we can actually see the words. A hydrogen compatible microchip and a lithium compatible microchip, and then somehow we got an A down here. Which is weird. I'm trying, right, so we saw this, and then why didn't it continue for the next, oh, maybe this output thing is not working right because of the warnings and things. Let's try it here, cargo run. Yeah, okay, there we go. Now we got everything. For some reason, bacon can get lost in terms of how much it printed. Okay, there it is. There it is. So each one of these is a separate floor. Okay, so actually, what we need to do is for each line, we'll create a floor. And then we'll just push it. And then, so we want to skip the letter A. And then if we see something with a dash, so that means we can skip 5 here. So we can say if let sum next equals iter next, else break, right? And then in here, let sum left right equals next dot split once. That is a stir and a stir. So if that worked, that means we have a microchip. And we can say iter.skip 1, 2, 3. And then we can say our item is the left string. So we can say floor.items.push item microchip left to string. If it doesn't, then we know, if there's no dash, then we know it must be a generator. So we can say skip 2. Oh yeah, I'm skipping over this and. So let me not skip these things. And I could just ignore the words. If next equals A, or next equals and, or next is equal to microchip. Oh, these have dots after them. Can I say next dot starts with? Micro, or next dot starts with gen. Continue. All right, and then we don't have to worry about the skipping parts here. And then we have either floor, either a microchip or a generator. Push item generator next to string. And then we can print the building. Let's see if this builds. It blows up. Xcoding. Thank you for the follow. Welcome to the stream. Did I do too many here? No, I didn't do enough here. That was a problem. Oh, and we can't compare stir with stir. Can I do this? Is that, or is that cheating? Okay. So, oh, and it's not printing up building. Why not? Oh, here it is. Yeah, it is. It's just not, there's nothing in it. Oh, did I forget to push the floor? Oh, this needs to be a while. Actually, we can do this. For next in words iter skip 5. That way we can get rid of this and this, because we're no longer doing a skip inside the loop, and we don't need to do that anymore. Right? Okay, let's see if that works. Nope. Can I do that? I can. And now this is looping forever. Oh, because I'm not moving to the next. Okay, now I have to kill it. Whoa. I should have grepped for target or something. I'll have to remember that. Get this in my history here. Grep target. There we go. Okay, so we're getting the words for ln lines. Wait, this shouldn't run forever. Maybe this doesn't work. Let's just try this. Cargo run. Yeah, it's just spinning forever. Let me print out what word it's trying to handle. I'm doing something wrong here, obviously, right? But I didn't think I was. So we're looping over all the words here, and then we should come back and do the next line, and then after all the lines are done, it should be over. That builds. Let's do cargo run and pipe into less so we don't flood the... It looks like it's doing the same... How many lines are there? Maybe I'm not splitting here correctly. Maybe these new lines aren't being new lined. Maybe that's the problem. Nope. What am I doing wrong? Processing L. Okay. FSC lines iter. No. Oh, yeah. Maybe this is the wrong way to do things here. Oops. There we go. Let's say let mod iter equals this, and can I do it this way? Maybe it's having a problem figuring that out. No, it's using the same string each time. This loop is never ending. Words iter. This is a vec, right? Yeah, it's a vec. So we should be able to iterate over the words. This won't work because this is going to be wrong now. It's going to generate generators for the first few words here. Which is wrong. What? I'm confused. What am I doing wrong? It's doing the same line over and over again. Doesn't this loop over the lines? And I'm splitting the correct thing. Oh, I'm never breaking out of this. So this loop goes away, actually. Wow, that was bad. I'm a terrible person, and I should feel bad. Okay. Words, iter, skip 5. So maybe I can do it this way. Len is 1, but the index is 4. Oh, right. We need to strip off the blank line, and I think I do that in my input reader code, so we can get rid of that. And that should hopefully. Can I do this now? Command error code 101, and it won't let me scroll. Oops. Len is 1, but the index is 4, right? Because it's trying to read an empty string. So if I do that, oh, it is coming up with a blank string as the second string? What? Oh, okay, so the new line wasn't necessary to add. Okay, let's try again. There we go. We still don't have a floor, but I think we're able to at least parse everything this time. So let's figure out where we push the floor. After we're done all of this stuff, then we say building floor push floor. And we can actually do that here and say if this is not equal to nothing, then we can put this inside the loop, do that, and now we should have a building. All right. Wow. Okay, and we got to turn off those print statements. Okay, and then, yeah, so this bacon's killing me here. Let's do that. And then elevator, let's just do this for now. Yeah. Okay, there we go. So the 0th floor, which is the first floor, contains hydrogen microchip, a lithium microchip. The next floor contains a hydrogen generator and a lithium generator. The next floor has nothing. Oh, and then we're missing the final floor because there should be 4 floors. I guess we should hardcode that. Or we can generate 4 floors right off the bat and then just add to them. Yeah, I wonder, maybe part 2 is like, okay, now there's a 5th floor. And so if we hardcode a 4th floor, that might be painful. So maybe we could create this here. Impl building new self, generate a self with floor. Oh, we want to pass in how many floors there are. So that way it's not hard-coded. Floors, new size. Vec bang floor semicolon floors comma elevator 0, and then I guess we don't have to store the floors as a separate variable because we can just say floor.len to get it. Oh, floor default. Clone is not implemented. Clone is not implemented. Okay. So now we actually want to say building new. Yeah. And give it 4 floors. And that should give us, oh, we don't, yeah, now we don't want to push this floor here. We want to say building dot floor of, which floor are we on? F. Building dot floor of F, and we can just, oh, just enumerate that, right? Right? And we don't push it here, and we're done. Did that work? I have no idea if that worked. Oh, yeah, now we can oops, clean up floor. We no longer have to create a floor here. Okay, so the 0th floor has the hydrogen and lithium microchips. The next floor has the hydrogen and lithium generators. We still don't have the, wait a minute. 1, 2, 3, 4. Okay, so it is working. And it was working the other way as well. So that was a waste. I just misread it, didn't I? Let's just double check here. We have a microchip and a microchip. The next floor has a hydrogen generator. The next, yeah, that's what I missed. I missed this thing here. The next floor has a lithium generator. And the top floor has nothing. Nothing relevant. Okay. So we're now parsing. How long did that take? 35 minutes to figure out how to parse this input data. Let's see if we can parse the actual data now. If I do this and then change that to an underscore, we should be able to parse out this thing. Right? So the first floor contains a Promethium generator, yes, and a Promethium compatible microchip, yep. The next floor has a cobalt generator, a curium generator, a ruthenium generator, and a plutonium generator. Next one has a cobalt microchip, yep. A curium microchip, a ruthenium microchip, and a plutonium microchip. And the 4th floor has nothing. Perfect. Okay, so we're able to parse both the test data and the real data. Okay, so that's a good, let's lock this code in by committing it, git, because I'm anticipating this being a multi-stage process here. This is very complicated, unfortunately. Status, git add. Oh, we can do git add input, git commit -m 2016 day 11 input. What was it? No verify? I don't have it anymore. Okay, and then git commit. Oh, git add source, git commit, no verify. Oh, oops. And now I have to look up how to modify nerd fonts. How to modify git modify last commit message. I always forget how to do this. Git commit amend. -16 day 11 input is what I meant to do. Oh, no verify. Git log. Okay, so now it's correct. Let's do a show on this. Git show. Yep. Oops. Git status. I did everything, didn't I? Okay, so now we're going to have to modify the input and parsing. There, git log. Okay. All right, so now that we can parse out the input, now we need to figure out how to make moves, right? Because if we're going to use Dijkstra to solve this, we're going to need to be able to generate the next state, all the possible new buildings from the existing building. And maybe that could be part of building, right? We can say fn moves self, and it can return a vec of building. And then we just generate new buildings with, and each time we generate new buildings, we have a new state for it. Like we can move HM up on this, in this case. Oh no, we can't move HM up. We can HG, HM, LM. Yeah, we can move HM up. That's what they have here. And that's all we can do. We can't move LM up. And according to this, the elevator stops at each floor. So we can only go one floor at a time. Anyway, we can't just go right to floor 3 or right to floor 4. So that means that the number of possible new states is fairly limited. The thing is, though, that with Dijkstra, we're going to want to be able to see if we've used a state before and ignore it because we've already considered it. This is sort of a modified Dijkstra where instead of having all the states up front, we kind of generate the states from the current state and add them to the queue to process. So we have to be able to look to see, did we consider this state before? And if not, then we can add it to the queue. And if we have seen this state before, then ignore it because it's already either been handled by the queue or going to be handled by the queue. So how do we create new moves? We have to know what floor we're on. We do, the elevator. And then we have to know all the items that are on that floor. And then we have to create a valid floor state. Right? We have to be able to look to see, is this floor valid, right? Because if I move LM up by 1, we have to be able to verify this floor is now an invalid floor because we can't have a lithium microchip and a hydrogen generator at the same time. That's not a valid state. We also have to be able to say, is it possible to move something off? Right? Where's a good example of that? Yeah, here, for example, I can't pull the generator down by 1 row because then we have a hydrogen microchip and a lithium generator at the same time. If I understand the rules correctly, what are the rules? So we can have pairs. We can have a lithium generator as long as there's a hydrogen generator attached to a hydrogen microchip. What would be an invalid state? So you can have all generators, you can have all microchips, or you can have lone generators as long as the microchips are paired. Solitary generators as long as the microchips are paired. Can you have microchip? Yeah, you can have microchips on their own. All right. So what we need to do is create. I think one thing that would help is just write a convenience function here, which determines whether or not a floor is valid. And then what we can do is we can scan through. And what would be good is if we wrote some TDD for this. Let's get rid of this. Let's write a test. Empty floor is valid. So what I want to do is create a floor. Let f Oh, we can just say this. Assert bang floor default valid. Right? And then we can put the test over here. We can run our tests. Oops, what did I do? Oh, all right, I need to return. I'll just return false for now. Okay. All right, good. Oh, and let me put an underscore on this thing so that goes away. And then we on line 11, we're not using the debug output for building. Really? I thought we were. Yeah, right here. Oh, right. This is happening because elevator, the floor for elevators never read. So this is kind of the debug formatting prints out the elevator, but elevators never actually used. So maybe that'll fix both problems. Yep. So let's do that. And then test data should never, oh, okay. I could do that. Come on, 10 tilde. There we go. Test data. Okay, so now we have a clean, good. And this is failing. So I guess what we can do is just add a test for this. If self items is empty, return true. Okay, so that test worked. And then what do we want to also be able to test for is if items are paired, then it's a valid floor. Okay. I'm just trying to think of, so if every microchip has a generator. Okay, so this floor is valid because there's only microchips on it. This floor is valid because every microchip on it has a matching generator. Maybe this would be simpler if I split up these things here. Because I could say if there's only microchips or if there's only generators, then it's a valid floor. If there's a mix, then every microchip has to have a generator. So what if I do this? If I say microchips and then generators. And because then what I can do for floor validity is say if the microchips is empty or gens is empty. Right, and that'll still be true for oops, right, now I have to say okay, floor micros and floor gens. Yeah. And that'll allow me to put microchips and generators separately, and then we can check if both have entries. If there's some microchips and some generators, then every microchip has to have a generator. But if but there can be lone generators, so we won't care. All right, so let's see. Test. Floor has only microchips. This should be valid for only microchips. Oh, let's create a floor default f.mics micros.push item. Oh, this, I guess there's no reason now to have it as an enum. We can just put strings in here. right? Because I have to say now item microchip foo, for example. And then assert f valid. And that fails because, because it's a string. There. Okay. And then the floor that has only generators has the same basic. See, now I have to say gens push generator. Okay. So that works. The next thing is that a floor with pairs pairs are floors with pairs. Let's do that and just say let mod f equals floor default, and then we can push a generator and a microchip, and then that should be valid. And I think that's going to fail because we don't have the code for that yet. F.valid. And then the other test I want to do, this is the wrong way to do test-driven development, but I'm going to do it anyway. Floor without matching generator is invalid. So if I do this state here and then add micros, push item microchip bar to string. I think that's an invalid state, right? We can have a generator on its own, but we can't have a microchip on its own if there's another generator on that floor. What did I do wrong? This. Okay. And then this should be invalid. And I missed something here. Oh. Okay. And that's at line 133, which is this guy here. Yeah, okay. So now we just have to write this part here. We're going to loop over for m in self micros. We probably have to do this so we don't take ownership of them. And now we want to see if the item is in the generator. This is n squared, but we're only talking about, what, 5 different things? So g in self gens. We have to find the matching one. If let found equals, we can do a filter, right? We can say self gens dot iter dot filter on g. And now we have to compare the items. So we need the strings. Okay, so this is where we want to do this. Yeah, we'll just change this to a string. And that's going to blow everything up, but that's okay. Check for generator to do. Okay, and now everything blows up because now we're not pushing these, we're just pushing strings. And then for all the tests as well, item. Okay, that wasn't too bad to fix. We have 5 warnings because we're not using that thing. Right, and now we're not yet implementing. Okay, so now what we need to do is we want to filter for the microchip, and this is now a string. Yeah, so all we have to do is say if self-gens.iter.filter x, g is the thing, g equals m. all I want to do is see if there is one. I guess I can say count. Is there another way to filter just to see if it exists? That's all I care about, is if it exists. Equals 1. Actually, if we want to say if it equals 0, we want to return false. Otherwise, we can return true here. Doesn't like that. No implementation for string compared to string. If I do that, will it work? Okay. And yeah, now we can get rid of this item business. Yeah, okay, so this passes. So this is how we test to see if it's a valid floor. So now we have to say, we have to be able to make a move and then check the building. And the way we check to see if the building is valid is we check all the floors. So why don't we make a test for that? Test building valid if floors valid. So we're going to say let mut b equals building new with 4 floors. Yeah, and we can just say, we can just check the validity this way. b.valid. They'll all be empty with empty floors. So they should all be valid. And now we just have to write this. Fn valid self bool. We can just loop over the floors. If every floor is valid for f in floor, if not f valid, return false. No, this is not the right way to do it. Because now I've basically written it. And then that should pass. Okay, and now we should be able to put a valid floor in the building. Thing with valid floors. Okay, to building, and then we're going to say b dot floor of 0 dot push. Oh, micro dot push foo string. Oh, and then we have to change this code here. We expect beta valid micros and mute. Okay. All right, and now I want to create a test with an invalid floor. Building with invalid floor. So what we can do is floor 0 is now valid. Let's put this on floor 2 just to be different. B dot floor, did I do that right? B dot floor of 2 dot micros. All right, so now floor 0 is valid, but floor 2 is invalid. So we should be able to say this is not valid. Okay, so that passes. So now we just need to be able to generate moves, and this is going to be the hard part. This is probably going to take up the rest of the hour, just generating the moves. All right, so to generate moves, we need to create a bunch of different buildings with states of having moved, right? We're going to take the current elevator's location. We're going to remove 1 or 2 items, right? Is that the limit? Am I remembering correctly? You can carry it most yourself and any 2 RTGs or microchips in any combination. Spacewalk, thank you for the follow. Much appreciated. Welcome to the stream. At most yourself and 2 RTGs or microchips in any combination. Right, so you can only take 2 things at a time from a given floor. And the floor we're going to take it from is this, where the elevator is pointing. So I think we're now ready to, oh, I should write a test first. Let's write a test first. Generate one move. Right, so we were looking at this state here, and there's only one move you can make from this state. You can't move the lithium module, microchip, because it'll blow up when it's on the same floor as the hydrogen generator. So the only move you can make in this state is moving the hydrogen microchip to the same floor as the hydrogen generator. So we can set this up as our test, and we might have to just make a little function to do that, because I might want to do that for multiple tests. So b.floor of 0.micros.push hydrogen string, and then we'll also push lithium. And then on floor 1, gens push hydrogen, and b.floor of 2, gens push lithium. And then we want to assert that we get one move back. I don't know if I want to dig into the details of the move. Let b move. I can't just call it move because of the move is a keyword. b.moves. So this will generate a vec. Oh yeah, we don't have it yet. B move len. Let's just do that for now and see if we can at least come up with a single move. Right, so we don't have moves yet. So let's write it. Moves self vec building. And actually what we can do is just say vec new and make sure the test is working. The test should fail because we come up with 0 and we're expecting 1. Okay. Let's see. So we want to get the current floor, whatever floor the elevator is currently on right now. And that floor is going to have a number of microchips and generators in it. Maybe I can ask the floor for a list of all the items. Because I just want to loop over each item and then say move it up or down if we can move up or down. And then I also want to say move pairs up and down if we can. So I guess we can say let items equal self floor of self elevator dot iter. You can chain iterators together, right? Rust chain iterator. And that way, after you're done with one, it'll, yeah. So we should be able to do that. Chain self floor self oh, it should be this should be micros. Vator gens iter. It didn't like that. Vec new. Oh, because we don't have elevator yet. Let's fix that right now. Okay, so that works. So we can now chain our way over all the microchips and all of the let item equal in items. Oh, for item in items. So we wanted, let's consider just moving one item now, and then we can move pairs of items after that. Arcatrim, thank you for the follow. Sorry, I can't say your whole name. Okay, so if self elevator is greater than 1, greater than 0, we can move it down. Move item down by 1. And then else if self, I guess we could just do this as a separate if, just to make it clean. Elevator is less than self floors len minus 1. Oh, self floor len. Then move item up by 1. All right, so that's the basic structure. 0 Zeta 4. Thank you for the follow. So how do we do this? So what we do is we're going to clone a building, clone our current self, remove the item from the current floor, this item, put it on the floor below us, and then check to see if the building is valid. And if so, then it goes onto our answer list. So let mut answer equals vec new. And we just put answer down here. So here we're going to say, how do we remove? So we're going to clone the building. Let building new equals building clone, self clone. Can we self clone? We don't have that capability yet, but that should be derivable. Right? Then we want to say new building dot elevator, there we go. Moving it down by 1. We're going to remove the item from the current floor, so new building dot floor of self elevator. Okay, so this is where maybe we don't want a vec, maybe we want hash sets, because then a hash set would be easy to just say remove. But here we actually have to remove it. And I'll just write a piece of code that says remove it, right? From the floor. That's a little wonky, but fn remove mut self s item string and we have to say what we're removing it from. Are we removing? Oh, right. We need to know if it's a microchip or so maybe I want to put that all back. Maybe I want to keep the fact that it's because we lost the information as to whether it's a microchip or a generator. All right. Live and learn. Derive, debug, clone, I guess. Enum item microchip string generator string. Doesn't like that because I broke something else. Oh, I never finished remove. Let's just do that for now. Okay, and now this is all going to fail because all these tests are going to fail because they're no longer so I have to put all of this back. But at least the test should show whether or not I did the conversion correctly. And then this is a microchip here. This is a microchip here. Oops. And then we have a microchip here. And that's a generator. That's a microchip. Okay. And now we'll do the generators. Item generator. And then I have to put in the closing closing paren on all these guys. Right? Like that. That goes there, and there, and there. It's a lot to switch back. Okay, and then when we parse, we need to do it here as well. Item microchip, and then item generator. Yeah, so now we need to know, now we know what the type of the item is. Oops, except I need to change the floor back to item. There we go. And it almost got it right. Mama Jufrey, thank you. Thank you for the follow. I missed a close somewhere, didn't I? 176. Here. Oh, I missed the item microchip on it. Item microchip. Oh, right. And then remove takes an item. Oh, now we can't do this filter, right? We actually have to convert the generator to a microchip and compare, or the microchip to a generator. Let match. I can't use it. Matching pair equals m dot generator, and then can I do that? And then in item, I can just do that. Impl item fn generator self returns an item, or self actually, and then this says match. Let's call it opposite, because I can say match item microchip s m is item generator m. I don't know what I'm doing here with the syntax. Generator becomes microchip. Is that good enough, or is that gonna, do I need to like clone the thing here? Yeah, so that's a string, so I can just say clone. Just make a copy of it. And then generator doesn't exist, opposite. And then this becomes if G is equal to the matching pair. Oh, and then we have to implement EQ, right? This is AOC item, and sorry, this is item, and this is a reference to an item. So if we can do that and that should remove those two things. And now we have to implement EQ. There. And now to remove an item from a floor, all of that just to remove an item from a floor. Where is it? Where's my floor remove? Here it is. Down to the bottom. Okay. So if the item is a microchip, then we want to filter on the micros, otherwise we filter on the gens. What is, there's a function in VEC which allows us to keep if or something like that. What's that function that lets you filter out items from a mutable vector. Retain, that's it. Retains only the elements specified by the predicate. We're trying to remove, so we can say match item. If it's an item generator, whatever, then we can say self-gens retain G, where G is not equal to item. And if it's a microchip, we say micros retain M. M is not equal to item. Is that going to give us a reference thing? No, that worked. Okay, but there's a warning here. Oh, because we're not modifying answer yet. Well, let's modify answer. So now we've removed the item from the floor. We need to insert it. New building, floor, new building, elevator, dot, insert item. Okay, now let's write an insert. Because I don't want to have to figure out there whether or not we're inserting what we're inserting. Self, item. That's fine. The formatter will fix that for me. And then for here, we just do this, but instead of saying retain, we say push item. Push item. And that fails because, oh, we have to clone this. Look at that. Okay, so now we're able to create a move. Oh, we have to first check to see if new building valid, then answer push new building. Does that work? I think so. And then move up by one is the exact same code, except instead of subtracting one from elevator, we add one to elevator. So maybe we can simplify this. Oh, look at that. It passed the test. Amazing. All right, so we can simplify this by just moving this out. And then just modifying if it's greater than 0, then we can move it. Oh, we want to, oh, that's right. We need to do this both times anyway, because it could be in the middle. Yeah, so we could end up doing both of them, or we could end up just doing one of them depending on where it is. Okay, so it's a little frustrating. We can extract this maybe as a subfunction, but at least the test passed, which is nice. That means that we're generating a single move. One thing that would be nice, maybe this would be a good time to do it, would be to print out the current state of the building, non-debug mode, or in a pretty print way. Display self. So we can say for floor in 0 dot dot self floor len rev. All right, I'm reversing it so I can print out the top floor first and then work my way down. Yeah. So the first thing we need to do is print out the floor. So we can say print bang F, and then F plus 1. If F is equal to self elevator, print bang space E, else print space dot. And what I can do here is say b dot print and then b move dot print. And then just make this the wrong answer. And then we should be able to see the error here. Oops. Oh, I think I have to do this, right? Oh, it's display, not print. Oh, be move of 0. Oh, and I forgot the new line. Okay, that's fine. But we're getting there, right? So we can see that the first one we have the elevators on floor 1, which is what we're expecting. And the second move, the elevators on floor 2. Good. So let's make sure we put the new line here. We don't need the quotes, right? You can just do that. And now for each item, oh, on the floor, but now we've split it out. For item in, I guess we could just chain them together. That's not a problem, right? Self floor f dot micros dot iter dot chain self floor f dot gens dot iter, and we can just print out the name. Actually, what we can do is just say item dot display, and that should do it if we create a display on item. And all this is going to do is print out the name of the item and whether or not it's a microchip or a generator. Display self. And this will say match self. Item microchip M. Print bang M colon M. I'm not printing it out the same way as the problem text. Oh, I guess we should put a space in front of each one of these guys. All right, but we can see now, we started off here with the same layout. Hydrogen microchip, lithium microchip, hydrogen generator, lithium generator, and then the second state has a lithium microchip, hydrogen microchip and generator, and then a lithium generator, and the elevator moved. Okay, so now we're able to display these states, so that'll be really useful for debugging, I think. We can get rid of that, we can get rid of that, we can get rid of that. Although it's going to complain about the fact that we're not using display, isn't it? Brr. Okay. Maybe I can just call it at the end of my parse function then. Where's my parse function? Instead of saying building, we can just say building.display. There, now it's called. And if I run, we should see the... Oh, right, we're still doing test data. Let's switch these around. And now we see... Oh, I see. The Promethium... Okay. Is that what it said? Yep. For that, cobalt generator, curiatum, yeah, so all the generators there and all the microchips there, and then nothing on the fourth floor. Okay, look at that. So I think this is a good bit of code to check in, although we haven't called moves or opposite or valid. Okay, what we can do is we can make these just put those in a test bin, and then opposite. Yeah. Oops. So we still need valid on floor. I was a little overzealous with the test. Oh! No, it's not that. It's that there's something else that needs to be... this needs to be CFG test as well. There. Okay. And then we'll put the test data back. There. And then we can run the tests. Good. Let's run, and there's test. And all the tests pass. Yay. Okay. So that's stage 2 is now we can generate... Oh, we can't generate all of them, right? I only did these singles. I didn't do the pairs. So we need to be able to move pairs of things as well as just single things. So how do we move pairs? If we have a list of all the items, which we do, then we can index them, right? It's a vec, right? Oh, it isn't a vec. I can collect it into a vec. I put too many colons there. I can't. Oh, I forgot that. Vec item can't be built. Oh, sure. Let's do references. There. Okay. So after that, what we can do is we can say for I in 0 dot dot items len -1, for j in I +1 dot dot items len. And now we want to remove 2 things. But we use the same exact code. If self elevator is greater than 0. Rather than typing this in again, let's just copy and paste. But now we want to be able to remove 2 things. Instead of just one thing. So we're going to say remove items I and remove items j. And insert items I and insert items j. And then we want to do the same thing for if the elevator is less than the floors. What do I call it? Self floor len, like that. And then, oh, right, this is moving down, so that gets a minus, and that one's moving up, so that's a plus. Okay. Can I write a test for that? We should be able to look for a state here where we move 2 things. Right here, actually. This next one, we should be able to move both of these guys up 1. And that should be one of the states that we find. I don't know how to write a test for it. But we can find out. Let's do this. Generate double move. Can I do this any simpler? Any simpler? Can I add something to floor which will make this easier to do? I'm going to, because this is my code and I can do what I want. So I'm going to say config test add microchip. Sure. Mute self, and the name is going to be a string, and then we just say self micros push item micro. Oh, we could just do an str here. Row chip name to string, and that way we can just put it directly, and then we do the same thing for generator. right? And then that simplifies this code here. We should be able to say floor add microchip hydrogen. And that should still pass all the tests. Oops. I want items, not item. Okay. Oh, right. And then we have expected natural. I was just trying to see if this would work here. And it should, but okay, so we're having some failures here. 39 move occurs. Oh, right, because I'm looping over this item list twice. So I have to make sure that we don't try to steal all the items. Can I do this? Iter? Yeah. And an add generator is not used. But I thought I put a... Oh, in the test code. Yeah, so I should be able to say add generator hydrogen. 325. Okay, so we just broke it because this came up with... Oh no, that's... It came up with 3 moves. That's not right. What are the 3 moves that it found? For B, M in B, move. Println, move. M dot display. So it came up with this move. That's not a valid floor. Oh, I broke. See, this is why I'm glad I wrote tests. I broke this over here, didn't I? It's not able to check to see if these are valid anymore. Is my floor validity checker wrong now? But that's the only test that's failing, right? All the floor validity checkers are correct. Let me comment out the double move code. Where is it? Here it is. Let me comment this out and see if that's where the bug is. No, it's coming up with 2 moves. And it shouldn't be coming up with 2 moves. It shouldn't be moving this the lithium microchip in with the hydrogen. Why does it think that's okay? Okay, well, and it's just the one where I did this part. So okay, let's see if I can do that. A floor without a matching generator is invalid. So let's see if we can say f dot. Let's add microchip. Foo. Right. And then f dot add generator. Foo. And then add microchip bar. Okay, and that should be microchip. Microchip. Yeah, okay, that fails. Oh, did I do something wrong here? No? Oh, I did, gens. Duh. Okay. Okay. The test is passing now. That's good news. We can get rid of this for loop. And now we want to be able to generate a double move. So we want to take this state. We want to take this state. This state can move both items up by 1, right? So that's what we want to see, if we can find that. If it can find that. So let mut b equals building 4 b dot floor of 0 dot add microchip lithium. Floor of 1 is going to have the hydrogen microchip and the hydrogen generator, and then the floor 2 is going to have the lithium generator. And we should be able to come up with, let's just call it moves, as B moves. We should be able to come up with this move here. It shouldn't try to move these both down, right? You can't have a microchip. If there's a generator on the level, it has to have a matching microchip. The microchip has to have a matching generator. I'm still getting confused on that, aren't I? But so there should be, from here, there should be a move that can move the hydrogen generator up by 1, or both of them up by 1. So there should be 2 moves. So here's where we're going to put the for loop in moves. Println move, and then mDisplay, and then we're going to say assert bang false, so we can see whether or not the moves came out. Oops, I meant to do a test and then wrap. Okay, so we didn't get any moves. It should have been able to find something to move down, right? It should have been able to move the hydrogen module down by 1. So let me have it figure out which ones are not valid. Println checking new building display, println valid. Okay, and we can see what those look like. Oops, and of course I broke all of them. So it's checking that. Let's say starting with println starting with self display. Oh, 351. Oh, 351. Yeah, that's not what I'm starting with, though. Floor 0. Oh. Oh, yeah. But, oh, the elevator's on the wrong floor. Ah, got it. B.elevator equals 1. Got it. Okay, it found a whole bunch of moves, apparently. So that one's valid. And this one's valid. Right, moving the generator up 1 or moving the microchip down 1. Those are all valid moves. And so printed out here, the 2 valid moves. So now we need to be able to come up with the double move. All right, so let's get rid of those printlns and the displays, because the bug was the fact that I wasn't putting the elevator on the right floor. Okay, and that should do that, and we should just see the two possible moves. And now we need to come up with a double move, and that was this code here. And now there's a third possibility going from here to here. Hydrogen, lithium, hydrogen, hydrogen microchip, which is this middle one here. Oh, there. And then the two generators. And then the lithium microchip is still on the first floor. Okay. So now we're able to come up with all the moves. Now we just need to write Dijkstra, but I'm out of time. So maybe tomorrow will be Dijkstra. Did I do all the tests I need to test? I probably did. I think this is good enough for today's stream. And then tomorrow what we'll do is we'll come up with, let's just, right, I need to figure out how to validate the fact that we did a double move. I want to be able to see that we have at least one floor with hydrogen, lithium, hydrogen on floor 3. Let mut found is false. There. Instead of doing that, we can do this. And M should be a building, right? So we can say on floor 2, micros.iter.chain. How do we do this? I want to see if it has a hydrogen generator. I guess we can just do this because micros should just have one item, should just have the hydrogen. So we can say len equals 1. And then the floor 2 gens is 2. Actually, we want to say if. And for now, let's say found. We're just checking the lengths. And I guess that's fair enough for Advent of code work. Let's see if Clippy has anything to say about our code. Clippy's happy. Very nice. So what did we do? We did a bunch of stuff. We can now generate moves. That's it. And we added a whole bunch of code to the floor, and we're going to remove these as soon as we start writing the real stuff. We're going to remove the test stuff. That's just there, so it builds without warnings. Git commit -am can now generate moves, valid moves. Right. So it's source, bin run, then AOC 2016, and then AOC 2016-11. Okay. Now that's in my command history finally. So what we did last time, the last thing we did was we figured out how to generate these double moves. In other words, moving two items at the same time, like these two. And in fact, maybe we should do that. Maybe we should just, of course, right now what I did was I checked to see if we could make the second move. Right, the second move being the one here where we move hydrogen generator and a hydrogen microchip up 1. But now that I'm looking at this thing, I'll scroll to the bottom here, and the last move is moving these two microchips up 1. So that would be a good test, right? To write a test to make sure we can go from this stage to this stage. And actually, when you're in this stage, there's two moves you can make, right? Well, you can move, actually there's more. You can move this one down on its own, you can move this one down on its own, you can move both of them down on their own, and you can move all of them to the top. So let's just write a test that will check that we can do that. Generate double microchip move. And it's, oops, didn't need to do that. Let's do this, because this is going to all be the same. And then we just change where things are. So the lithium microchip is on floor, the third floor, which is 2 here. The hydrogen microchip is also on 2, and then 3 and 3 for the generators. Okay, we generate the moves, and now I just want to see, is there a move for m in moves if m.floor3.micros.len is equal to 2, and m.floor3gens.len is equal to 2. Now I'm thinking, should we just verify that all the other floors are empty for I in 0 to 2, 0 to 3, because we want to check 0, 1, and 2. So to check to see if all these floors are empty, we just have to look at each one. That's all. And then we have to count. I guess we need to determine if they're all empty. Oh, we can set found as true here, and then check to see if, as soon as we find one that's not empty, we set found back to false. Okay, so oh, that's a panic situation. So we should assert that m.floor of i.micros.len is empty. Right, because if we end up with more chips than we expected, and then we can just say break here, and then just assert, bang, found. Okay, so that'll show us that we got this move, and let's see if that works. Over here, we can do our tests. Yep. Okay. Save. And it failed. Okay, so that's good. I'm glad we tested that. Let's find out what move is failing. So let's print out starting with, and then we say b.display, and then we'll say checking, and then we say m.display. And now we can see what moves it's finding. Oh, it didn't find any moves at all. That's not good. There's no checking here at all. So let me make sure I set it up correctly. Hydrogen lithium generators and hydrogen and lithium microchips. Yeah. Okay, so I set it up correctly. So that means we have a bug in our moves code. All right, let's fix that. Oh, maybe we have a bug in our valid code. Because I imagine it's creating the different buildings. Checking if this is valid. New building dot display. Println it is. Else println it isn't. Okay, and then we'll do the same thing here. Actually, I could have done it just here because this is the one that will generate the move up. What did I do? I did something wrong here. There we go. So then there's println it is, tis, else println it isn't. Okay. So let's see what this does. Got to spell it right. It didn't even generate any. Really? Not a function. Of course it isn't. Oh, am I not calling it? It's right here. Oh, here it is. Generating moves, and it's not generating. It's not seeing any moves. So all the moves it's trying to make are invalid. Oh, I think I know why. When we check this, this should be gens is empty. Right, for this floor. I was thinking, oh, well, we're checking here in the microchips to make sure that there's a paired generator with it. But there's generators is empty on this floor. So they should all be valid. But it's not even, oh, it's not even getting to the point where it's checking. Okay, there's another bug somewhere. FN moves, there. So we go through all these items. And then we should come here. Let's print out what the items are. It's empty. Oh, there we go. We have a bug. Oh, right. Of course we do. I forgot to set the elevator. The elevator should be on the 3rd floor. Right here. That's annoying. All right, so this should work now, and then we can remove all those printlins. Yeah, okay, that works. Good. Never code after you've overslept. Get rid of all these printlins. Get rid of this. Get rid of those. Make sure test still pass after we deleted all those prints, and it does. Okay, good. So we're able to generate the final move now. We can go from here to here. So I think the next thing to do is try to figure out how to implement Dijkstra for this. And that's where we need to have this little cheat sheet over here, because I always forget how to do it. And then all we need to do in part 1 is call Dijkstra and say how many moves it took. And this one, actually, I think we can change this. I changed this to add Microchip left to string. I think that's all I need to do. If I say run here. Right. And so now if I say save, it should generate the same output. Oh. Oh, right. Right. Because I put that there. Okay. And then add generator next to string. There we go. And that should generate the same. Whoops. Oh, right. We don't need to string it anymore. Yeah. Okay. Good. So that simplifies that code a little bit, and then I can change all these, but I'll do that afterwards and clean up. Okay. Dijkstra. Test. Can find final move. All right, and we're going to set this up exactly the same way, except we're going to remove the display part, because we know that part works. And now, instead of saying let moves equals b moves, let's create a Dijkstra search. Let mod d equals Dijkstra new, and that'll contain all the data that we need to store for Dijkstra. Let me pull it up again. There we go. It'll contain the dist, the prev, the q, and all that kind of stuff. Or maybe the q can be local. I don't know. Actually, all this can be local, can it? Well, all right. I'm going to do it this way anyway, and then just say d dot find building, and that'll just return how many moves it takes. And I'm going to do an assert q. It should take one move to find the final from this position. Right, this is the second to last position, so it should take one move. And of course, Dijkstra doesn't exist, so if I run tests, this should fail. Okay. The reason I'm pulling it out as a separate struct is that I want to make this, eventually I want to put it into my general utility belt. So I'm going to do this. Just separate it this way. And then say pub struct. DIJKSTRA. Yeah, and the question is, so then we'd want to put a type on it. But for now, I'm just going to use building. And I think what we want to do is use hash maps for these, which means that building has to be hashable, which will be interesting. Right, because I think I want to say have dist be a hash map of building to index. Because what we have to do is we have to generate these things on, kind of on the fly, and then keep a list of them, or yeah, we keep a list of them somewhere. Like we have this index that we generate all these hash map holding U size, and just this contains the index. Well, we'll see. Let's try to implement it and then see. For now, we'll just keep this empty, and then I'll just say pub. Sorry, impl extra, and this will just be find. Pub find self, and then a start would be a building, and it'll return the count of how many entries it found. And for now, let's just do that. Oh, it's going to complain that it doesn't need to be mutable. The reason I'm putting mute on there, oh, there's no new. Okay. Let's derive default. And it just say Dijkstra default. There. All right, this fails because we're returning 0 and we're expecting 1, and we're not using find. Oh, it's a public interface. Private type is a public interface. Oh, yeah. Okay. So for now, we'll just do that. And I probably have to do that if I'm going to stick building in there. Okay. So how do we want to do this? So the first thing we need to do for Dijkstra is set up this vertex graph, right? But we only have the starting position. We have to generate them on the fly, so it's sort of a modified Dijkstra. And then dist of u. So u is a building, right? We're looking at each building. So here's the way I'm going to do it. So q is going to be equal to a hash set. I don't know if I have hash set here. Building is hash set new. And this is going to fail because I don't think building is hashable, and I don't. Oops! I just tried to jump to the definition of it. I don't have these here yet. So let's add these here. Use standard collections, hash set and hash map. We'll do both of those guys. And this should fail. Oh, yeah, because we're not using these. Oh, okay. It seemed to not complain that building is not hashable. I don't have hash on it, but maybe it is. Okay. I'm not going to complain. Maybe it can derive hash from that. All right, that's fine. So then we want to start off Dijkstra. by inserting on the dist. The prev is going to be useful for debugging, so maybe we will do that anyway. But it's not useful for figuring out the length of the path it takes to get to the end. But let's put it in there anyway. So we can just say we can create a dist. So this is where I was thinking maybe the dist would go in here, but maybe we can put it here. Dist. Dist is going to be, let's say, a hash map from building to usize, like I said before. Hash map new. And then prev is going to be building to building. All right, because what prev contains is buildings indexed by building, and it stores buildings, and that way you can backtrace back to all the previous buildings and get your shortest path. And then we need a place to store the buildings as we generate them. So, and that was that index I was talking about before. So that'll be a hash map from building to usize. Okay. And then we're going to insert into the index the start at index 0. And then that's that line there. Oh, we have to do add v to q. So dist of v, which is the only vertex we have, we'll get the same thing. Oh, so we have to clone these. Let's clone these out. 0, and then the prev. Oh, undefined. Okay, so we make that undefined. Let's make this an option instead. So this will go from start to clone to none, like that. And then that's that. And then we're going to add v to q. V is the only start thing we have here. So q insert start clone. All right, so that's that one. That's this loop here. And there's no loop because there's only one thing to insert because we're generating them on the fly. Dist of source gets 0. So that's that line. Maybe we pull that out because we don't want to set it to infinity and then add it later again. So this is the setup here. We do need actually to keep track of the index for this guy here. So we're going to say let occur is equal to 0, 1. Because we'll insert 0 and then the next one will be 1, and every time we insert a new while not q is empty. And we're going to do this here. U gets a vertex in q with min dist u. So it starts off here, right? So it starts off at the source. But we have to do a search. So we're going to loop over q and save the best one. So this will be usize max because we're trying to find the shortest distance for u in q. And v is equal to dist get of u dot unwrap. It should be in dist, right? And that's a building. Oh, that's a reference to a building. Is that going to work? Well, let's find. Oh, yeah, because you pass in a reference to the item that you're searching for. That's right. If v and v should be, it's unknown. Oh, maybe because I did that. It should be a u size, right? because dist has, oh, maybe I need to close this. It's still unknown. All right, I'm going to comment out this line here. I don't want to call find yet. Oh. Yeah, see, that's what I thought. It lets you define the variable, but doesn't actually let you do the insert. So I think we need to derive EQ and hash for building, which probably means we have to do it for floor as well, right? Partial equal EQ. I think you have to do that first, right? And then for floor as well. Where's floor? This is floor, yeah. Oh. Oh, we need it for item. Okay. So now we're able to do all of that. Fn find. Let's complain we're not using it. That's fine. Okay, so now it should tell us that V is U size. Yes. Okay. So now if, oh, it's a reference to U size. So we can say if V is less than best. We have to make it a reference as well. Or we can start. If star V is less than best, then best is equal to star V. And then found is found. We need a found. Let found equals none. Because we found the shortest distance so far. Sum u.clone. And then we have to assert that found is not none. And so this becomes u by the algorithm, right? So we're implementing line 10 here. Let's do it this way. That way we could preserve the variable. Let u is equal to this disaster. And then what I can do is I can say found unwrap here. And that'll assert that'll assert that we found something. And put a semicolon there. And now u should be a building. It's an empty thing because I forgot to take out the semi there. It's a building. Good. Okay, so now we have a building that's the shortest distance. So that's line 10. Line 11 is q.remove. That's an easy one. Should we assert that that actually works? Because that would be a bug if we... yeah, we're finding it in Q. It would be a bug if we tried to remove it and it wasn't there. Let's do that. Hash rust hash set remove. I think it returns true or false depending on whether the item is in. Yeah. Returns whether the value was present in the set. So we're going to assert that it was. So if it's not able to be removed because it's not there already, we'll just panic. Println. Panic. Tried to remove you from Q, but failed. Okay. So that's just a safety thing in case I have a bug up here. All right. So then the next thing to do, this is where this thing here, so we can terminate the search after line 10 if u is equal to target. So line 10 is this block of code. This is line 11. So we can terminate the search here. If I say up here, let mut target is none. And down here I can say if u is win, and I have to write that obviously, then we can say target is equal to u, some u, break. Okay, because then we found our win condition. And then down here we can just, how do we figure out Oh, the way we figure it out, the count is we look at prev. We walk the prev thing, which is this business over here that we'll get to in a minute. Okay. Now we're going to go for each neighbor, v of u still in queue. So this is the tricky part. This is where we actually have to insert new entries into queue based on our current state. So u is the thing we're going to check. And now we have to generate the moves and add those to queue if we didn't already consider them. And the way we know if we didn't already consider them is because that's where this index comes into play. So every new entry we insert into index, whenever we generate a move, we check with index to see, is it in the index already? And if it is, then we can skip this move because it's already being considered. The reason we can't check in queue is because we remove from queue as soon as we find it and start to play with it. So index is a permanent list, and queue is our current working list. And it's a modified Dijkstra, like I said. Okay, so we can say for m in u.moves. Now these are buildings. It's an m building right there. I don't know, it's probably hard to read on stream. What we'll do is we'll say for each neighbor v of u still in queue. So we have to check to see if it's in queue first. So if q.contains m, here's what I'll do is I'll be fancy here. And I'll say let neighbor, if it's in queue, then we're fine. Then we'll just use it directly. Else we have to check with the index. If it's not in the index contains m, then we have to insert it into the dist array. We have to pretend we had inserted it up here, and we have to add it to the index array. So the first thing we do for the index, we'll do the index array, index insert, m.clone, cur. We have to increment cur. Right, this will get it into the permanent index, and now we have to insert it into the distance array with infinity. So we'd say dist.insert m.clone usize max. That's our infinity, and then we also have this prev, right? Dist.prev. Oh, sorry, dist.prev. Prev.insert m.clone none. So that gives us that. We also have to insert it into queue. We don't want to forget to do that because it's got to be considered in our search up above, and we only look in queue, so we have to say queue to insert mclone. Yeah. Oh, we do need to say else here because we're doing this if. We do need to do something here. What do we do here? If it's in queue, we return it. Oh, we have to return it here, m. If it's not in the index, we insert it into the index and return it. And insert it into the index and into queue. So now it's in queue, and we return it. If it's not in queue, and it is in the index, that means we ignore this state because we've already considered it. So we'll just continue for the rest of the moves here. Hopefully that makes sense. Yeah, we're not going to return dist.prev, and then let's see what happens if we save this. I can't do usize max. Oh, because I put a dot there. Right, I have to write isWin, so let's do that next. And then these need to be ampersanded. Oh, contains key, right? I'm getting there. I'm getting there. This is more complicated than than you think. Okay, so impl building. Let's go to the end of that and write a function called isWin self and returns bool. And the win condition is basically everything's on the top floor. And we know the top floor because we have the length of the floor array. So for I in 0 dot dot self floor len -1, if oh, do we have a floor is empty? Check. That would be nice. We could just do impl floor. And we have add microchip add generator. We have a valid, which we're going to have to take the config test out. Remove insert. Let's do an is empty on self, which is bool, which is going to be self dot gens is empty if there's no generators and no microchips. Self micros is empty. Right, that's all that is. And now up here in the isWin condition, we can say if not self floor I is empty, return false. And then we can say if, oh, yeah, if every floor is empty except for the top floor, let's call that a win condition. I'm not going to bother checking to see if there's anything in the top floor because that would be an assert debugging thing. Okay, so that's the isWin. Let's see if that allows us to help build. Assign twice to immutable variable found. Well, that's an easy fix. Now we're on here. No method name moves for found for struct building. Really? Oh, you know what? Because I did that. Okay. And a remove, right? Okay, this is where we now have to fix all these things. Because now we're actually calling these functions. I should be able to do it this way. Valid. Okay. Valid, valid. Okay. And then this guy. Opposite. Working our way through. Okay, so we have 13 warnings because we haven't finished implementing Dijkstra yet. Let's get rid of that one. This is never used, is empty. I thought I was calling it, this is on floor, right? Yeah, I'm calling it in building, in isWin here. This is saying isWin is never used, isWin. I'm pretty sure, yeah, it's right here. Oh, maybe because I'm never calling find. I'm never calling find. Okay, maybe it's time to put these back then. There we go. And right, okay, now we have to deal with the neighbor, let neighbor. Okay, so now that we have the neighbor, what do we do with Dijkstra? Each neighbor V of U. Okay, so maybe this is V instead of neighbor. We'll call it V. We'll just follow the Dijkstra variable convention here. Alt gets dist of U plus graph of edges U comma V. Well, what's graph of edges U comma V? It's just one, because all we have to worry about is one step between each move. So that's the easy part. Let alt is equal to dist dot get U, get ampersand U, right? Because U is a building. We have to kind of remember to reference it for that. Dot unwrap plus 1. So that's this line. That's line 14. Line 15. If alt is less than dist of v. Well, what's dist of v? Dist of v should be whatever we pull out of dist here. So we can just say let dist sub v is equal to dist get v. Is v a reference? No, it's not. So we have to do that. Unwrap. And it should be set to umax when we get here. So it should always exist. And then we can say if alt is less than dist sub v, then we're going to replace whatever was in there with alt, right? So dist insert v.clone, comma, alt. And then prev insert v.clone with some u.clone. Is nert. There we go. That should be all of the first part of Dijkstra. That should find the target. And target is some u, right? So we can just say target.unwrap.display. And we can see if it actually found the state from here, from this second to last state. Did it find the state? It still returns 0, so it'll end with an error. But that's fine, because then it'll print out the final state, and of course this failed. Oop, target unwrap with brackets. Oh, look at that. So it did find the final state. And it took one move to do it. That's great. So I should be able to just say, oh, right. So here's where we need to get tricky. We actually have to walk backwards with on the previous list and count how many steps it takes to get there. And if we can count how many steps it takes to get from the previous back to the starting position, then we know how many steps it took to get from the starting position to the end position. So we have to figure this out. But I'm excited because it was able to actually find this the target. Let my count equal 0. So this will be the count of how many steps we take. Let's take a look at the algorithm again, because I think it's just using prev to index the previous. Yeah, if prev u is defined or u is the starting state, while u is defined, insert u at the beginning of s. We don't need to do this part. S is will be displaying, or will keep a track of, be an array of the steps, but we don't care about the actual individual steps. We just care about the count. So while u is defined, u gets the previous version of u. So I can say let u is equal to right, and then we want u to be able to be an option, which means we need to unwrap it each time. So because we're pulling it out of prev, and prev stores options, right? It doesn't, oops, that's not good. I dragged the text and it pasted it for me. Very, very helpful. Okay. Some target.unwrap. And then we can say while if prev u is defined or u is equal to source. We can say while let some something state is equal to u. We're going to keep looping and modifying u as we walk backwards. We'll say count plus equals 1. And then u is equal to prev dot get state. Ooh, what is state a reference or not? It is not. So I need to put a reference there and then unwrap. And this is unwrapping the get, not unwrapping the thing that's in there. So you should still be an option building. And then we're done there. And then all we need to do is return count. Is that all we need to do? Of course not. Mismatch types. Okay. This is an option building. Oh. It's a reference. Okay. I thought I had it. Oh, no. I want this to be the reference. Duh. Okay. Yeah, okay. It's up 10 warnings because we're not calling it. And it failed. Panicked at index out of bounds, len is 4, but the index is 4. And that was on line 91. -1. I'm surprised that our... Oh, because I never tested. That we can move down from top floor. Let's do that. Because that way we can... Where's our first building? Building with valid floor, building with invalid floor. Generate one move. Test. Generate move from top. And this should fail. Let's comment this test out. Which will generate a ton of warnings because we're not using find now. That's fine. Here we go. So let's create a building. We'll set the elevator to the top floor, and we'll put something on the floor, I guess. Add microchip foo, and B floor. Add generator foo. And then we should be able to say it can make 3 moves, right? It can either move the microchip down 1, the generator down 1, or both of them down. B moves len. And that should fail. Oops. If it compiles, it should fail. Right. Generate move from top. Okay, so now we need to subtract 1 off of this guy here. And that should fix that failure condition, right? And it does, and now we can do this. Left is 1, right is 2. It found 2 moves. Oh, yeah, it's an off by 1 error. Okay. I'm counting each state, not counting each move. So, okay, let's just fix that. Right, because there's always 1 fewer moves than there are states, right? We have a starting state and an ending state. It takes 1 move to get there. I counted 2 states, right? So it's truly the fence post issue. We're counting the connections between the fence posts, not the fence posts themselves. Okay. So that worked. So we're now able to solve this basic problem from the last step. So we should be able to do this one then, right? We should be able to say, okay, solve it from the second to last step. Or should I just go whole hog and use the starting condition, which is right here. This is the starting condition. And see if I can find the solution. Can solve example. Can solve example problem. And I guess I didn't need a Dijkstra to be a separate thing. It would be nice if I could make this Dijkstra code take the type generically, and I think I can if I just define it to be hashable. Let's see. I should be able to say assert EQ 11 is equal to Dijkstra default find B. And maybe I just get rid of this Dijkstra thing and just have it as a separate function. I don't think I need to save any state. What did I do wrong? Oh, I have to call default. It found it in 10 moves. Did I set it up wrong? Or is this if I set it up wrong, then there's a bug in my Finder, because I'm sure that 11 is correct. Somebody would have said something a lot sooner. Oh, I did set it up wrong. Floor 0. There we go. Floor 0 gets the microchip, the 2 microchips, hydrogen generator on the 2nd floor, and lithium generator on the 3rd floor. Okay. Now it says 18. Ooh. Well, that's fun. What in the world? Okay, well, what we can do is, as we walk through our states, we can print them out, and then we can look in reverse order to see where things would go wrong. Where's our find function here? So our target is the starting state. Target.display. Unwrap display. Oh, I can just say u.display. No, I can't. Target.unwrap. Display. Println. Starting state. Println. Next state. Oh, ending. Yeah. Ending state. And the next state is going to be u.unwrap.display. And then that blows up. Oh. Okay. Oh. Okay. I wonder if I can do that here as well. So I don't have to clone it. Yeah, okay. Come on. Trying to be fancy with my keys here, and I'm failing miserably. Ref. There. There. Okay. Oh, now can't find the final move? Oh, if let. Oh, if u is sum. There. Because that's right. We end when we hit none. Okay. Oh, and I put ending state after. That was dumb. All right, I just want to be able to read it. Ending state is here, next state is there, next state. Okay, so now we can work our way through the problem, starting with the starting position. Oh. Did I have the elevator on the wrong floor? I do. Okay. Oh! So that's it. Okay, good. Good. FN find. Let's get rid of these displays. Make sure it still works. And it does. Okay, I think we are at the point where we can solve the first problem. If I say cargo run. Oh, duh. I actually have to put the code in there. Who knew you had to call the code? Okay, so output. So we have the building. So all we need to do here is say Dijkstra default find self. Oh, we're not storing the building in the. Yeah, okay. Building is an option building. And that way, when we create it, where's the new? Oh, I have to say none here, right? I have to need to look for this. There we go. A building is option building. Right? Okay. And then I got to finish writing that part of the code. So this is self.building.unwrap. As ref. Okay. So now cargo run. Option unwrap on none value because I didn't put it in the building because that was dumb. All right, so you can just say self building is equal to sum building. Do I have a building default? I do have a building new. So let me not make this an option because that's kind of annoying that it's an option. Buildings. Self. There it is. Building new 4. Let's just do that and then we can overwrite it after we've done here. Like that, and then we don't have to do this. 3 warnings. Oh, display is not used. Okay, yeah, we're just using display as a config thing right now. Okay, I'm not going to worry about that part. Okay, so using the test data, it found it in 11. Let's use the real data. Uh-oh. Okay. We have a combinatorial explosion here, don't we? I wonder if doing it in release mode will go faster. Although we shouldn't have to go to release mode to get this to solve. All right, so I think from what I remember, and it's been a while, what I remember is that the trick here is to avoid states that are essentially the same, even though they're different. So I think the trick here is that a building, I'm going to let this keep running while I'm talking. A building can have like this state here, right? It effectively doesn't matter where the items are, but how many of the items there are on the floor. Because they're all interchangeable in terms of determining what new states exist. So this is a different state than these two are different states because the count of generators and the count of microchips is different on each level. But I think if we swapped around G's and M's, it would be essentially the same state because it would still take the same numbers of moves. So for any building state, if I swapped HM with LM, it wouldn't matter. If I swapped H on this one, it doesn't matter because they're on the same floor. But if I swapped HG and LG, it wouldn't matter because it would be the same number of moves required to solve the problem. And I think we can kind of cheat without making a lot of code changes if we make the floors hash the same if they have the same layout. So if each of the floors has a similar layout in terms of how many generators and how many microchips, I just need to look up how you do a custom hash. Rust struct custom hash. How to implement EQ and hash. Or we might have to implement EQ as well. Or partial EQ. How do you do a hash? You get a hasher which has a state, and you add the things to the state. Okay. I guess I could have looked that up in the docs, but Stack Overflow was faster. So let's modify floor. Here's floor. And we have to implement hash. Where does hash come from? Standard hash. Okay. So up at the top, use standard hash, hash and hasher. And then in floor, we'll say impl hash for floor. And it's fn hash. H is a hasher. I'm just copying this code over here. It takes a self and a state. It doesn't return anything. And all we have to do is say self dot micros. All we care about is the len, the number of items in there. And we just call hash on that with the state. And we do the same thing for gens. Okay, so now the floors will hash the same. And that way when we compare, then we want to change these to, instead of vectors, we want to change these to hash sets. What's that going to blow up? If I do that. Okay, this is going to be a little more complicated than I thought. And then we have to implement EQ, right? Because EQ has to match hash or partial EQ. Impl EQ for floor. And I forget what the function signature is, but we'll find out in a second. As soon as I delete that. And that. And then it tells me what the function signature is. So I can just do that, get rid of that, put that there, delete until we see a tick, grab that. And then RHS is always self. Oops, I missed that. Yeah, okay, so now this is going to change all this stuff here. Instead of saying push, we do an insert. Okay, we do the same thing here. Oh, that's interesting. Now we have mismatched type. Oh, because these things actually return something. Okay. All right, that wasn't too bad. So now we have a thing here. We just need to implement the EQ, otherwise it'll blow up. So this is if self micros len is equal to other micros len. Because all we care about now for floors to be equal are the lengths the same. Self gens len is equal to other gens len. And get rid of the if statement. Okay. It's not complaining too much. The warnings here are the display issues. Oh, I guess not. Oh, I have more than one display. Okay. There. Okay. So now what happens? Does it explode? 33. That seems low. Wow. Okay. I'm in shock. That's the right answer. I thought it would be like a couple hundred moves based on the search space we were looking at. But okay, 33. I'll take it. Is there anything I want to clean up before I commit these changes? I guess the only thing I would want to do here is change Dijkstra to just be a function. Because we don't, there's no data we need to store here. So I can just say function find Dijkstra, or Dijkstra search, let's call it. And then we can get rid of that thing there, reformat, and then change the tests. So we just say Dijkstra search B semicolon, right? And then find. We just have to change this one as well. Dijkstra search. And then this one here. Get rid of that. Dijkstra search. I'm getting good at spelling the word Dijkstra. Oh, it doesn't need that anymore. Okay. So now let's see if that still works. Oops. I didn't want to test everything. Oh, right. All our tests blew up because I changed. Okay, I'm not going to run the test just yet. I'll clean that up in a second. Cargo run. Let's see how quick it goes in debug mode. Okay, 2.8 seconds, and in release mode, takes longer to build. Less than half a second. Okay. So I'm pretty happy with this then. Let's commit these changes. Git status, git add source, git commit -m 2016, day 11, part 1. Oh, right. Okay, let's clean that up. Let's make sure the code actually works in test mode. So we can bake in this thing here over here and hit test, and we can fix all of these push. gens.push. Every place there's a gens.push, we just say add generator foo. Guess we can, oops. Add generator foo. Oh, there's a lot of these. Okay. Oh, I want to do this. CFG, add generator. Oh, okay. And then we can get rid of the 2 strings, right? We don't need those. Semis. Okay. And then what about, oops. Oh, that's right. We get rid of the gens. I forgot. Okay. And then for all the micros, micros.push changes to add microchip. Okay, and then f.gens. There's a few of those, right? Yep. Oh, only one of those. Okay. Oh no, here's one. Okay, so that's those, and I think I need to remove some 2 strings. So let's take a look here. 2 string, yeah. Actually, let's search for .2 string, and that way I can say df. Ooh, d2f that. There we go. That makes the test code look a lot nicer too. Oh, I got to fix those. Let's go look for item, : : Yeah, here we go. Add microchip theme. Okay, let's see what happens. 179. Oh. Did I delete too many 2 strings? Okay, and now the tests work. Let's check in with Clippy. Does Clippy have any comments? It does, has 1 comment. Not bad. We don't need an ampersand there. Perfect. And the tests still work even though I took out the ampersand. Good, okay. Git commit -am 2016 day 11 part 1. Very good, very good. Okay, now I'm scared, but we're going to take a look at it anyway. Continue to part 2. Part 2 is you step into the clean room separating the lobby from the isolated area and put on the hazmat suit. Upon entering the isolated containment area, however, you notice there's some extra parts on the floor. A lyrium generator, dilithium generator, and dilithium microchip, and lyrium. Okay. These work just like the other generators. In Microchip, you have to get them up to assembly. Okay, so it's just adding more work. So if you found a pretty good but not great solution, this will make it worse. So you need to actually have that one solution with the trick where all you have to do is count microchips and generators instead of treating each condition as a separate state. So for part 2, we don't even need to write a test, do we? We can just say let alt is equal to self building clone. I don't want to touch the original building, and then I'll just say alt dot. Ooh. And it's on the first floor or on the ground floor? First floor. Oh, but here first floor is 0. Okay. Alt floor 0 dot add microchip. And the name doesn't matter, does it? I'll still put it in there because we don't even print it out. They just have to be and this becomes dilithium. And then instead of add microchip, we change this to add generator. And then we just say alt. Dijkstra search. Alt. Okay, well, the test passed because I didn't add a new test for it. I guess I could have just run it from Bacon here. But right, it runs in debug mode, so it's going to be slow. How impatient am I? Cargo run, release. We'll have them on competing cores here. 57. So it took 2.4 seconds here in release. Oh, I can't really compare because I was running other stuff. 20 seconds there. 57. Is this right? It's the right answer. Huzzah. Okay. So git status, git diff was what I wanted to do. And that's all I did. Git commit -am 2016 day 11 part 2. All right, it's slow, but it does the trick. I wonder if there's something faster than Dijkstra that will work for us. I don't know how we could do hinting for the A* search, if that would work any better. Or we could probably speed it up using a priority queue instead of, right, because all we need to do is get the one with the lowest distance. I'll leave that for a future endeavor. All right, so that's day 11. Should we peek at day 12? I do have time.